Let's talk about data locality in Kubernetes. As far as persistent workloads and stateful applications go, ensuring locality of data storage is somewhat of a challenge and a unique one to Kubernetes. That we have a few new features in Kubernetes that allows us to address, and that allows other platforms to interact with. So, let's talk about data locality itself. So we have the ability in Kubernetes to provision resources in sort of a flat model, in which we can simply request that a deployment be created, and it will be created on whatever nodes the scheduler sees fit. Similarly, we will need to connect actual storage objects into pods that exist, say, for example, in a stateful set. And we need to ensure that this happens in an optimal way. It is all too easy to have a manifest of stateful sets not specify anything about locality, or have your actual storage class not specify anything about locality and get suboptimal placement, resulting in a lot of network activity, whether it be local in the cloud, and an increased storage latency. So there are a lot of barriers to this, because this is making a lot of assumptions. Data placement is one that data can be as close as possible to that workload as you would like, and in some cases that's not always reality. And especially in composed infrastructure, some nodes are more capable of some things than others, and there is often a trade-off for storage capability and compute, or any other number of factors. So we have a few things to balance. We have data access, throughput, and latency, which is always extremely important for whatever application stack you're using, typically. So if you're running high-performance workloads, then we care about latency. We don't just care about latency of the storage system itself, we care about latency across the entire stack. Latency between applications, and latency from applications to their backing storage. Now, because we don't necessarily always have data centers or systems or whatever we're using to actually host our application workloads, we don't always have a homogeneous environment. So we have a question of whether we have nodes that are capable of delivering that much storage to their workload in as low a latency situation as possible, which direct attached is the lowest latency situation you could hope for in most cases. And we have the idea of composability, in which case we actually have many different applications that have, say, vast storage requirements that need to be placed dynamically that can't necessarily follow a local copy, or can't be constrained to where a local copy exists. And the overhead of making another copy available over there beforehand is unrealistic. So we need a storage orchestrator. There are quite a few out there. The CSI plugin for Kubernetes allows storage vendors to interact with Kubernetes in a way that is out of tree. So we have the ability to plug into a standard interface. So we have quite a few software-defined storage systems out there. So what we want when we're talking about locality is one that is able to better ensure locality. So we'll talk about LINSTOR. LINSTOR is an SDS system. It was originally designed to provision DRBD resources among nodes. But what it has become over the years, and especially with the integration of Kubernetes, is that it is a control plane that manages Linux storage objects of all kinds. We have a separate control plane that's accessible via a REST interface that we have a CSI plugin for, that you can use with a command line, or etc. And we can provision local and or remote storage with this. And not just because it is a DRBD provisioner, but because it is also an LVM provisioner. It's a ZFS provisioner. It provisions all of these storage objects that you're familiar with in Linux and presents them to, in this case, Kubernetes, to your pods. And so because of that, it has very, very close to no overhead, especially when considering block transports like DRBD. It's very little overhead, close to none. So we have a system that will allow us to ask Linux nodes to provision data storage that we can generally trust, because it is using existing constructs for storage that we're already very familiar with, that we already know that are very stable. The architecture of it is actually fairly simple. We have a single controller. That controller can be made highly available, but for the purposes of the architecture itself, we connect to a single controller. That is because that controller makes connections to many different satellites. What a satellite is either a daemon, or brought up by a traditional init process like sysvinit or systemd, or in this case, it's a daemon set in Kubernetes running on every one of the nodes. And what the satellites do is they actually orchestrate these commands to storage. They're the things that are setting up LVM. They're setting up DRBD. They're specifically privileged in order to do so, as these are kernel abstractions. These are actually in-kernel storage objects. So, because we have this REST API that we can use to connect to the LINSTOR controller, we can manage storage in a cluster that we otherwise normally wouldn't be able to do. Right now, say for example, we have a series of LINSTOR satellites, all with a logical volume manager installed, and maybe two of them have the same volume name. One of them is a different volume name, and the reason why we would do that is to classify storage. We can very easily classify storage from node to node or inside of nodes by simply specifying a different name for a volume. We can create a volume group and say that this one is fast, this one is slow, this one is NVMe, this one's not. This one is actually backed by memory, this one isn't. So we have this ability to use a volume manager, even though we don't have to. We could use a disk directly, though we commonly would use a volume manager. And we can stack any number of block features on top of those, such as bcache or VDO for SSD caching or inline deduplication. And then, because we're talking about Kubernetes, it's very common to want some kind of network transport for that storage, because we generally, for the most part, expect our clusters to be flat, to be able to run our pods anywhere would be ideal. And that is the ideal situation that we start off with when we begin using Kubernetes. And even though reality doesn't always match up with that, it generally is the first assumption until we have to define some sort of constraint. So in order to allow that sort of thing to occur, we have block transport systems. We have iSCSI targets. We're actually using the TGT backend or the LIO backend. We actually have an implementation selector. We have NVMe-OF, in which we can actually orchestrate the connections between NVMe-OF targets and initiators, rather than having to use a more complex REST-to-REST system. LINSTOR is already aware of the existence of NVMe-OF targets and initiators and is able to broker that connection. And then finally we have, by default actually, as it is agnostic to basically any other hardware implementation, DRBD as a transport. While traditionally that was a replication software, after a large amount of expansion and development over the past 5 or 6 years, it has become a fairly cloud-centric block transport system. So it is able to replicate data as well as provide that data disklessly in a client and server model. So we have all these block storage objects that we're familiar with that it can actually use. We can pick any one of these objects and go forward with it. You can choose your own adventure. You can use persistent memory with LVM, encrypt it with LUX, replicate it with DRBD, and present it with DRBD itself, or present it with NVMe OF. You could have an NVMe drive that's presented directly with NVMe OF. It doesn't really matter. It does storage in layers, and it arbitrarily stacks those layers. Though one of the things that it does is makes decisions about what can and cannot stack upon one another. For example, the placement in your block storage stack of LUX encryption matters. If you encrypt very early on and you have a deduplication system lower in the stack, that data will not deduplicate anymore. It's encrypted, it's scrambled by the time it gets to VDO. So LINSTOR makes intelligent layer decisions as to how the block stack should actually be formed, in addition to being able to be manually overridden, because why not? And so we have an SDS system that will allow us to ensure data locality, either through the DRBD system or by using storage in a more raw, direct manner, local storage, if you will. So we have an application orchestrator, and that's Kubernetes, right? But the problem with Kubernetes, it's not so much a problem as it is a fact or thing, is that stateful applications are a little more challenging than stateless applications, but that's always been true. Stateful applications are particularly vulnerable to noisy neighbor problems. We have a fair amount of resources that are consumed of a particular kind in a stateful application, and running CPU-intensive applications alongside that can sometimes be problematic. So we have a balance to make. Again, we want our applications close together so that our latency is low, yet also we can co-locate too aggressively. So we need some kind of standard way to ensure, or at least suggest, that workloads shouldn't be co-located so tightly, or should be co-located tightly. So, in order to facilitate that, we should be able to lift the restrictions of whether a resource should be tightly co-located or not so tightly co-located. It should be easy for an application to move to one place on another cluster and still get fairly low latency access to its data. We should be able to make compromises to move and make decisions between local storage and non-local storage. DRBD allows us to do that because it's a replication system and a block transport. You can actually have two replicas of data and access those data replicas as if they are local, so long as those replicas are stored on that node. Alternatively to that, if your application does move over to another node, that data will be accessed remotely while using two replicas in the DRBD resource as a highly available target. Similarly, we can use NVMe OF and iSCSI target initiators either locally or remotely, though we don't really have the ability to ensure locality again after they've moved. In a DRBD resource, we can actually move over to a remote node, a diskless node, and then make that data local again by populating the replica into that node synchronously while it's still accessing data. There is actually zero time, well, relatively zero time, between being able to mount the data and the process of copying the data beginning. They actually happen at the same time. We don't have to copy it first and then access it. We can gradually move towards locality as resources move. So we can take a look at this in a pretty practical way. We'll give an example architecture. It's fairly simple, but it's good enough to demonstrate what we're actually concerned with. And in this case, this is a highly available Kubernetes cluster with 3 worker nodes, each one in its own fault domain shared with a master. So the fault domain in this case is an availability zone. Each availability zone in this example has one node in it. This was done for a few different reasons. One, to illustrate the impact of latency with remote resources and how Kubernetes can optimally or suboptimally deal with that in some situations, and also to demonstrate that we can generally break availability zone barriers in regard to availability of data, to replication of data. So in this model, we have two pods that were placed. One is a database and one is a client application. The database has been placed non-locally to its data. The actual LINSTOR SDS is storing a volume on autoplace, and that volume happened to be placed on our middle node there. So this is not exactly optimal. We have two large areas of latency that we can sort of tackle. So we have application to application latency, and we have backing store latency that we can address. Application to application latency is somewhat easier to address than storage locality and latency. And we're reducing the path to where we get to our storage, but the way that we accomplish that can be pretty varied. For one of the easiest ways to actually pin nodes to a pod is with a node selector in Kubernetes. The node selectors are fairly simple. You can specify a label on your node, and then specify that your pod may only run on nodes with that label. And this is fairly strict. In some cases, it's sufficient, and a simpler method of defining your scheduling should generally be preferred over a more complex method if it does what you need it to. But a node selector is a requirement. We're saying that this pod can only run on a node with this label. And if there is no node with that label available, then it will have failed to be scheduled. And that's not always ideal, especially when we're trying to account for failures of infrastructure, failures in an availability zone, failures of, one entire different class of machine even. So we have another way to do this, and that is pod affinity and anti-affinity rules, and node affinity and anti-affinity rules. A node affinity rule is a lot like a node selector, with the exception that the language involved in creating the affinity or anti-affinity is much more dynamic. You can actually prefer that a node be scheduled on a particular label. Prefer that a pod be scheduled with a particular node label, I should say. You can prefer that a pod be co-located with a particular pod of another label. Now that's much more dynamic. That allows your infrastructure to be almost entirely replaced, and if all of your co-location relationships are inside of your pods, then you have a lot less to worry about with your storage. And you can anchor your stateful applications to particular different pods using something like a node selector or a node affinity rule, something a little more simple. And then use pod affinity and anti-affinity rules to bind pods together. So it's, while pod anti-affinity and anti-affinity rules are a little more complicated, they're certainly worth it, and the language is only marginally more complex. The real issue with pod-to-pod, interpod affinity rules is that they're scheduler heavy. It is a lot of work for Kubernetes to figure out that your pod should be co-located with a pod of a particular label, because it has to ascertain the state of all of the pods in that cluster, especially when you begin to make preferences more complex. A very complex pod preference can cause a lot of computational overhead in your scheduling system. The more pods it has to ascertain, the more pod status it has to get, Everything over here is going over REST interfaces, which are fairly quick, but I mean, we're making a lot of calls here. And again, the scheduler has a lot to compute there. It's a lot more heavy and time-consuming than simply specifying a node selector. You really shouldn't do it with any cluster that's beyond 100 nodes, something like that, and that's the point at which you should stop using pod affinity rules and begin using some other method, or at least slow down. Just take it easy. So then we have storage latency to address. None of that addresses storage latency. That addresses pod latency and allows us to pin pods to nodes, but we can't always guarantee that the storage is going to stay on that node. If a disk fails in a particular node, and we have a replication system that is generating replicas across several different nodes, it makes it very easy for this situation to show up again, where we have our storage remotely. So we want, ideally, for our storage to be local, at least within a fault domain, typically within a fault domain. It can be somewhat atypical to always be able to guarantee your storage is going to be on the same node. It sure would be nice, and you can certainly do that and enforce that, but it's more difficult. With the extremely low latency internode storage fabrics that we have, this is a lot less of a concern. I mean, we have InfiniBand systems. We have even node-to-node PCIe interconnections. We have extremely low latency capabilities, but we don't always see those in production. I mean, we want them all the time. We always want extremely low latency interconnects, but the lowest latency interconnect, even in consumer systems, is going to be at the node with very little extra cost. And of course, a lot less network overhead. So we would use, in this case, the placement protocols in LINSTOR in order to accomplish this. It actually is able to place storage dynamically, manually or dynamically. We can specify storage be placed based on node name. We can specify that it be placed based on various other node properties and labels, but also based on those default intrinsic node labels that are available in Kubernetes. And there's only a few of them. There's node, there's instance type, host name, availability zone. That's an important one, because that's what we use when we dynamically allocate in LINSTOR. We do it by the availability zone, by the fault domain. Because we assume that resources within a similar fault domain are going to have low latency connections to one another. They're at least not going over a WAN. We can usually somewhat guarantee that within a fault domain we have low latency network connections between nodes. So if we can manage to auto-place resources within a similar fault domain, then that helps a lot. And in this model, where we have one node per fault domain, well, obviously, it's always going to get assigned to that one node. And that's just because of the simplicity of the example. So we have that ability to place storage, but that doesn't always guarantee that storage is going to work well. We will have disk failures, we will have entire volume failures, and we need some way to make our applications highly available. Now in Kubernetes, there's a reason why I call this increasing durability and not increasing availability. Increased storage durability by replicating storage across nodes does not necessarily mean that an application will be highly available if it fails and is rescheduled on that other node. Depends on what your definition of highly available is. And a pod rescheduling time out of 5 minutes doesn't really fit many definitions of highly available. So if your pod does fail on one node, even though your data is durable and replicated, it can't just fail over. It's not like those high availability systems, those extremely stateful high availability systems that we use where applications can just go to another node. Kubernetes things are a little different. And you can tune that pod eviction timeout to be 1 minute if you'd like, at a minimum, but that's still 1 minute of downtime for your entire database, and that's somewhat troublesome in a lot of cases. However, increasing durability is never bad. You still want increased data durability, regardless of whether your application is highly available yet. So, in this case, data is available in 2 places at one time. It is read local in 2 places at one time because of the way DRBD works. If we actually were to move this pod over here and access data on this node, it would be able to read data from the local disks. Only writes are subject to the latency of the network. In a somewhat similar fashion, reads can also be balanced. This makes the assumption that your network link is faster than your disks, which can sometimes be the case, especially if you're using rotating media. Your network link is very easily faster, less latent than your disk, or even greater throughput than your disk. So read balancing across replicas is possible, not just in the case of failures, but for actual performance gains in some cases. Generally, you would want a separate fabric for your storage replication in that case, so that replicating doesn't impact your application I/O. So the replicas themselves are highly available. Sure. We still only have 1 database instance, though. And depending on what kind of database we're using, that can be a little problematic to solve, but there's plenty of solutions to this out there. So we're not too worried about it yet. If we look at what happens when the resource moves, this is what I talked about before, where we have DRBD that can access disklessly. If, say, that replica, your database was running here on this middle node and was rescheduled over here, then its data is still available. It's not unavailable. At any point in time, it attaches disklessly immediately. And it can still rebalance too. This is actually still this is not only a highly available target for storage, it's also a continuously available one. One of these replicas can go down and there's no concept of failover. It just simply uses the other replica. Same when they're co-located when your workload's co-located on one of the replicas, same deal. But in this case, both of those connections are remote to the node. And you can have many of these replicas, up to 32 in fact. Not that I've ever seen that or expect to see that. It's a high enough number. So, and this is one of those cases where we may not think that it's ideal, but within a single fault domain, we could actually expect to see this model quite often, in which we have storage nodes that connect remotely to your endpoint workloads. And of course, we can add another replica. We can specify that once diskless node should have a replica now. We can actually increase the replica count and bring in a local read replica to that node and just begin increasing read performance immediately at very little cost, very little complexity. So data is local in 3 places. This also gives us the ability to lose a lot more. We can lose quite a few more nodes, but also quorum is possible. Quorum in our storage layer is somewhat important, and that's for the purposes of avoiding split brain scenarios. While Kubernetes is still orchestrating these systems and has an idea of what nodes are active and what nodes are not active, it is still possible for a node to be disconnected from the cluster and the storage to still be active. Now, this is not really exactly ideal because whenever we have a replicated system that's disconnected, yet still has writes to it, we can't really know whether another storage replica is also connected somewhere and is also getting writes to it. So what we end up with is a not only split brain, but a divergent data situation, which in any data layer, whether it be structured or unstructured or backing, is extremely problematic. And in the case of backing storage, it's difficult to solve because we're not necessarily aware of the contents of that data that has been split. So the ability to vote between replicas as to which ones are effective, which ones are good, is critically important. And we need 3 nodes in order to do that. So we have quorum in the backing store. Sure. And we have more replicas. And this is really not very complicated at all. You can make just about any workload have more durable data this way. You could have a workload that's not even capable of running multiple pods have durable data this way. And that's going to become more and more common as legacy applications begin moving up to Kubernetes. There are plenty of implementations out there that specify a single pod stateful set is what their application runs on. And while this isn't completely desirable from a high availability standpoint, we still need to address data durability in an effective way. So addressing it 1 layer below that application at the storage level will certainly help. We'll allow that pod to be rescheduled, for the node to be lost, and for the data to not be gone. In a hyper-converged way, if you will. Or composable, doesn't matter. Well, we have all these applications that are actually able to run in multiple pods. We have, for example, MongoDB that's capable of running 3 pods, having 3 replicas, actually quite simple. So we don't really have to address things that way for most applications, and the ones that we don't have to address that way, it is better to replicate at the database level than at the storage level. There's no reason you can't do both. Replicating your storage underneath your application and replicating at the application level is certainly possible, though you wouldn't necessarily want to end up with 6 replicas of your data in most cases for financial reasons, mostly. So we want to make multiple pods, and we want to connect storage locally to those pods. And we don't really have to replicate it. And if we don't have to replicate it, and if we don't really need to make those pods available elsewhere if they need to be rescheduled, we can actually we can cut out quite a few layers and either have the SDS use raw disks to serve that application, since the application is handling its own replication and can tolerate the loss of a node, and also handle its own essentially replication to new pods that are created. We don't really have to worry about quite a lot of things that we would replicate data underneath an application for. Also, replicating at the application layer it has a few advantages. For one, your application's aware of the data. And this is what I spoke of a little bit earlier about split brain situations, in that they're very difficult to resolve when they happen in your underlying storage, because you don't really know what replica is good, which one has the data that you want. If we actually split a database, we're able to say, yes, this one has this replica, this one has this replica. We do a diff between the two. We're able to manually solve a merge. It's quite a lot easier than trying to solve a split brain at something a little more agnostic to the actual data structures, like the block layer. And of course, we have a little less overhead, because we don't have to transfer entire blocks. We can transfer just the messages that this application is sending, which in most cases are a lot smaller than a block being 512 bytes or 4 kilobytes in size. That as an atomic unit of transfer is sometimes a lot higher than you need. If you're sending very small documents, if you are making small changes to a database, you don't necessarily want to have to update 4 kilobytes every time, especially if it's highly transactional. Yeah.
Is it okay to ask questions?
Oh, yeah.
So why, you said split brain is less of a problem than replicating at the database. Why could it be that?
Yeah. It's, there's a hard problem with split brain resources in storage layers that aren't aware of the data. In this case, if we go back to this example here where we have block storage here that we have actually replicated, and we manage to create a split. The difference between, and we'll go back even a little bit, the difference between replica A and B, if they are truly split, is very difficult to ascertain because there's a lot of layers in between there. For one, we're not just making a block device connect directly to a database. We usually have a file system in between. That file system is going to be different on one side than the other. So then we have to essentially stop everything, look at each one of those replicas individually, and there's a lot more of a process for actually ascertaining what replica we do and do not want. And then when we want to resolve the split brain itself, if we're doing it at a block layer, one that's unaware of that actual application data, then the way they resolve it is to trash a replica. That's how they resolve. When we're running at a database, we don't necessarily have to just trash a replica. We can actually choose some records from one and choose some records from the other. And yes, we can sort of do that during a split brain situation. Before we trash the replicas, we can pick some from both of them and put it back together, but it's much more involved. It's generally more difficult because we have to we have to kind of bring everything down and look at it. A split brain situation can be pretty dramatic and generally should be avoided. The best way to not have to deal with it is to keep it from happening. It's to keep it from happening altogether. And quorum is one of those things that does that. What quorum will do is actually, if it either in this model where we have sort of a semi-quorum, one node sort of votes to maintain quorum, or this model where we have a harder quorum, and this applies to database applications as well. We actually have the ability to stop a split brain from happening altogether. Whenever these nodes disconnect, say if this system here were to become completely disconnected from the other two, it would suspend all I/O operations immediately. No new data may be written. These other two nodes could still continue to write data, and it would be okay. They still have quorum. And then when this third node rejoins, it will see that it's a data generation behind or two and be able to catch up, and hasn't had any data written to it since it was disconnected. So we can just say, yes, we've lost no data at all. We'll just catch up with the other two replicas and be on our way. As long as we can ensure that your replicas actually don't write any data when they're disconnected from other replicas, you won't get a split brain. You just need a way to make sure of that. And Kubernetes doesn't really have fencing yet. It's going to. They're looking at using the same fencing agents we know and love from the old pacemaker stack. But it's not there yet. So when we do have fencing, we'll have the ability to be able to ensure that our storage replicas don't get split. But until then, we need some way within our storage application or within our structured data layer to guarantee that data isn't written during a split. And quorum is the way to do that, as node expensive as it is. So we talked a little bit about the lower overhead of using databases, unless they're multi-master. Yes, that's a significant point to make. A lot of multi-master databases actually have a fair amount of overhead. They have to intercommunicate with one another. They require a fair amount of cohesion that using an active-passive model doesn't require at all. I'm just so nearsighted, I can't even read that. No matter anything to me. So then we have this model right here where we've established that maybe we have quorum through our databases, depending on which one that we're using, but at least we have 3 replicas, and we can lose any one in a case of quorum, or we can lose more than one in the case of non-quorum and still be okay. This is a good position to be in. Especially from a high availability position, we can lose one and not have to worry about constraints of availability. And also, losing one doesn't make your application stack go down. We don't have to reschedule your pod. This is where we want to be in general with Kubernetes. This is where we want your actual application to be highly available rather than your storage. So again, this can be a little bit lower overhead than using say DRPD in the background, but it often isn't if we're using an active-active model, which we so often are in Kubernetes. So this actually will involve sometimes more network overhead than simply replicating your storage underneath. It depends on what you're using. But it doesn't always look like that. Sometimes it'll look like this, where those actual databases that are running, they're not optimally placed with their storage. Or that is to say, in Kubernetes, their storage hasn't been placed optimally within. That's what happens. So what happens in this case? Well, we can sort of rearrange how these pods are running and pin the pods to where the storage is now. But it only got this way because the storage was auto-placed, and it would really be a pain to have to do that every time you make a new application, deploy a new stateful set, or deploy more storage volumes. So we need a way to make sure that this doesn't happen in the first place, and also that we can keep it that way. So we have two things to take care of: making sure that locality is there in the first place and maintaining locality. So how can we do that? Let's look back at our original example. Just one database, one replica of data, one application. We want pod affinity and anti-affinity, right? We want to be able to co-locate our applications with storage that is running on our node. When we allocate storage to a node, we can actually give that node a label. We can say this node has this storage, this node has this volume. That's a property that we can actually examine, and we can allocate storage that way. We can place storage that way. So in Kubernetes, when we're placing storage, or placing resources in general, the first thing that happens is that your pod gets placed. So if your pod gets placed first, then while we don't care about storage yet once that placement has happened. So we either need to control pod placement very strictly, again using something like a node selector or node affinity rules, which are more expressive, or we can make the storage show up where the pod is. And that's something that we can do with LINSTOR, with its storage class. We can specify that storage should be follow a placement policy. And a placement policy, again, can be manual or it can be dynamic. It can be based on node, it can be based on host name, or it can be based on some node labels and use node selectors in order to figure itself out. And one of those most important labels is availability zone, is a fault domain. So LINSTOR can place storage in the same fault domain automatically, and we don't have to do anything. We don't have to specify anything other than placement balanced. That's all we have to say is placement policy balanced. That's it in the actual storage class. And then it will provision storage in the same fault domain that your application is running in. So we have a way to make applications more dynamic using those same policies, and we have a way to bind storage to those policies. But we've really only talked about actually binding things together and not keeping them separate. What do I have? So we have a potential noisy neighbor situation happening here, depending on what these things are actually running. And Kubernetes takes care of this itself pretty well. It avoids a lot of noisy neighbor situations. We generally have an awareness of what our pods are going to do, of what resources we have available on a node. Even if we schedule a pod on a node and we have a noisy neighbor situation, we, upon rescheduling, can move that pod away. That's good, thank you. So, the problem is this only happens on rescheduling. It doesn't happen on execution typically. So if we actually manage to co-locate a noisy neighbor together, it'll be noisy for a little while until we actually trigger a rescheduling. And a noisy neighbor situation will trigger a rescheduling after time, and we will know afterwards not do that again. But we can keep that from happening if we know about it beforehand. So we can actually make a case for anti-affinity and say that this node should ideally not be placed with a node that has this selector. We should ideally not place our extremely CPU-heavy workload along with our database. Ideally not. And unlike the situation very much earlier, where we have a locally, a distant replica of storage that your database accesses, accessing a database over a distant link is a lot more ideal in a lot of cases. For one, there's less overhead because, yes, the request size is smaller. But also because we have all kinds of caching mechanisms, and they're built into a lot of cases. And we have essentially less of a demand for latency a lot of the time between application and database. It's understood. It's standard. So if we can understand how the stack integrates with one another, we can sort of figure that out a little easier. But your database transactions over to your storage, that's a little more, there's more of them for one. Those transactions happen a lot more often. We can make one big giant blob transaction to your database, and we don't have to worry about latency that much. And then that can result in many, many IOPS on the back end. So actually accessing it over determining where you want to link separate your workload can be extremely important. And in a lot of cases, if you have to, it would be ideal to separate your application from a link from your database if you have to. I think that about covers it. Anybody have any questions? I know there's a lot to discuss. Yeah?
So I came in a little bit late, so might have missed something you already mentioned.
Sure.
LINSTOR, is that generally available?
Yeah. This is all open source technology. You can actually just go on GitHub and try it out. And that's an important thing that I always forget because I work in the open source space. It's kind of a given to me.
Now, the unit of placement, is that an entire volume, or can it be something smaller than a volume? So, you can imagine that one database node is accessing, let's say, a few terabytes of data.
Mm-hmm.
Maybe as it sort of reorganizes data, it needs a little bit more space or something like that, and it needs, a slab of data from somewhere else. So I'm guessing LINSTOR does not allow you. It's not a true distributed logical volume management.
No, not too much. No, a lot of that responsibility is up to the application that consumes the storage. It's actually provisioning block storage to nodes. So while that storage is actually fairly dynamic, LINSTOR can resize it, but it can't necessarily grab some piece from somewhere else and make it available.
You cannot take pieces of storage from multiple nodes and make it look like one model.
Take multiple nodes and make it look like one volume.
It's not a cluster.
Yeah, it's you can take multiple volumes from different nodes and aggregate them. This is what's called a stacked model. You can make multiple nodes participate in creating one very large node, but this is an alpha feature. So it's not really something we would do in practice. This is actually a functionality of DRBD10. DRBD10 is not production ready yet. But it does actually have a concept of one erasure coding. And it will allow you to have, your actual replica span many, many nodes and have one very large replica. Not even in a stacked model. in an actual erasure coded model, and as well as a few other significant benefits. I mean, the feature list is long, and I haven't worried about it too much because it's so incredibly alpha. But it's there. It does work, but don't put it in your production systems yet.
So you're from Linbit?
Yes.
And is that the main contributor for LINSTOR?
Yes, yeah. Linbit is the main contributor for LINSTOR and DRBD. Yeah. That's one of the reasons why LINSTOR was designed to be the provisioner for DRBD. That's a good question. I like the question. Does anybody have any more? Yeah, go ahead. Yeah, absolutely. I'm happy to talk.
So, can you tell us about how it's being used? If it is, or are you in beta?
Yeah, it's actually being used as part of Intel's rack scale design project for one. That's the RSD project, the rack scale design project. It is a significant component of the persistence layer. In that particular model, the rack scale design project is, in a lot of ways, a very ideal and well-engineered path to success for hosting a data center. You can generally apply this model and have things be extremely efficient. And one of the reasons that it does this, one of the reasons that it can do this with storage, is that it serializes access to storage. They have these, this performance tier of persistent memory that applications actually use. And on a schedule, that performance tier is snapshotted. And all the changes that were made within that performance tier are pushed down to lower level replicas. And it's actually LINSTOR that manages the snapshot system. And that's a combination of DRBD features and LVM features.
Who is driving this RSD project?
Intel. Yeah.
So, I'll keep asking questions if nobody else. You have one. Go ahead. No. I think we're out of time. Oh, okay.
You can keep going until the next session starts, but the next session has to start on time.
Okay.
So you talked about how when allocating storage,
Yeah.
You can allocate it close to the database. But what about, let's say now the storage exists, and now it's a matter of scheduling the database node.
Right. Like if our persistent volume already exists, and we're making a persistent volume claim.
Now,
Yes.
right. Are there hooks into Kubernetes to sort of make that happen as well?
There are hooks in LINSTOR to make that happen. And assuming you're using DRBD, because that's how we're able to sort of heal locality, if you will. It actually has a migration feature. What will happen when you make a persistent volume claim against a volume that isn't stored locally is it will be accessed disklessly. And what that looks like is a DRBD resource that's lost as disk. It just looks. I mean, we made the color green where it says diskless, but it generally means a failure in an HA system, and that's what it was designed to do. Was to keep accessing data even though a disk has failed. So we're just doing this intentionally, and it works like a target and initiator relationship. And of course, we cleaned everything up around it, so it doesn't just say there's a bunch of errors. But what it can actually do is migrate. It will actually increase your replica count from, say, for example, from 1 to 2. Make data local to that node, and then decrease your replica count, removing the original. So we're actually able to migrate storage between places, between availability zones, and even across regions. It's synchronous replication, but it's also asynchronous replication. It can do both. It can be a regional data store. That's one of the main arguments for actually including DRBD replication in addition to database replication is that you can replicate passively your database storage to an entirely other region using a synchronous protocol, especially using DRBD proxy. That's a closed source product. It's our only one, but it actually does allow a giant in-memory buffer to pool all those changes and not be limited by the TCP send buffer. It's a streaming DR solution. So they would enable that. Same scenario too, especially if they're both controlled by the same SDS system, which in this case they would be. If they're controlled by the same SDS system with both sites, both your distant site and your local site are controlled by LINSTOR.
Do you need to give the speaker to set up?
That's our time.